Chapter 2, Exercise 17. Show that the following four conditions are equivalent. Condition A is A is a subset of B. Condition B is A minus B is equal to the empty set. Condition C is that A union B is equal to B. Condition D is that A intersect B is equal to A. Right, so there's many ways to go about proving that these four conditions are equivalent. One can show one by one that the conditions are equivalent, so we can go like A if and only if B, A if and only if C, A if and only if D, and so on and so forth for every pair of these. There is a less laborious way to go about this, which I like better. I call it the circular implication proof strategy, because the idea is that you do something like this. You have A, B, C, and D. You show that A implies B, then you show that B implies C, you show that C implies D, and that A implies D. And then you might be wondering, like, well, what about the backwards way? Now, if you look at this, if, for instance, we want to show that C and A are equivalent, we want to show that A implies C and C implies A, also known as A if and only if C. And what we can do is, well, A implies C this way, right? And C implies A right back this way. And we can do this for any pair, right? So A implies B, but also B implies A by if you follow this chain. So in fact, once you establish those four implications, what you really showed is something more like this. But you don't have to go through the tedious exercise of going through all of them. Oh, and of course, you also show these. All right, you get what I'm doing, hopefully. Anywho, I'm gonna shrink these, put them up here, and I'm gonna get rid of these, just so you get an idea of the idea of this proof. Right, so first we're gonna start with A implies B. So let's do this as we always do, or rather, let's call it assume A is a subset of B. Right, and we're trying to show that A minus B is equal to the empty set, right? Now, A minus B is equal to the set of things X such that X is in A and X is not in B. However, if you look at this, since A is a subset of B, if X is in A, then X is necessarily in B. So there are no elements that condition that there are no elements X such that X is in A and X is not in B. So A minus B contains no elements and is thus the empty set. There we go. That's one knocked down. Now we're going to do that B implies C. So let's assume A minus B is equal to the empty set. And we're trying to show, again, that A union B is equal to B itself. Okay. So now by exercise 2-11, A union B is equal to B union A minus B. But, of course, A minus B, we assumed, is the empty set. So it's going to be B union the empty set, which is just equal to B. Simplified, this is A union B is equal to B, which is exactly what we were trying to show. All right, now we're going to show that C implies D. So let's assume that A union B is equal to B, right? And we're trying to show that A intersect B is equal to A, right? So to show that these two sets are equal, we want to show that they're subsets of each other, as usual. A intersect B is a subset of A, and A is a subset of A intersect B. Now, A intersect B being a subset of A is trivial because if X is an A intersect B, then it has to be an A. So all we need to show is that A is a subset of A intersect B, which may not always be the case, but let's see if this assumption helps us get to that. Right, so consider some element X in A. Right, so if X is in A, then X is going to be in A union B. Then by assumption, A union B is equal to B. So X is going to be in B, right? Thus, X is in A and X is in B, meaning that X is going to be in A intersect B. So, indeed, A is a subset of A intersect B, and thus A is equal to A intersect B, which is exactly what I wanted to show. You know what, just for consistency's sake, let's swap these around. Cool. And now the final step, which we don't want to forget, is that we also have to show that D implies A right back. Right, so let's refresh ourselves on what A was. A was the condition that A is a subset of B. Okay, so now let's assume that A intersect B is equal to A. Now let's consider X in A. So if X is in A, X is in A intersect B. So X is in A and X is in B, right? So X is in A implies that X is in B. Thus, it follows that A must be a subset of B. And there we go. So, you know what, just for completion's sake, let's do this and write them all out. The proof is done. That's our proof. But I'm just going to write them out a little bit neater. It implies that A minus B is equal to the empty set. It's going to be A minus B equal to the empty set. Implies that A union B is equal to B. Then this is A union B equal to B implies that A intersect B is equal to A. Oh, I wrote this wrong. There we go. Did I write it like that over here? Okay, cool. And finally, A intersect B equal to A implies that A is a subset of B. Cool. Now, these are some kind of weird facts to, I'm just going to put this on this page too. Weird facts to know, I guess, but it's nice to start establishing equivalences and identities, equations, if you will, theorems, because once we establish that these are true, then we can solve more difficult and more involved problems by, if we ever find some question where we have to assume that A is a subset of B, then we can say, oh, since we solved exercise 2-17, then we also know that A intersect B is equal to A, and so on and so forth. You can use any of these from now on once you've proved them. So we'll see if we end up using them anytime soon. But for the time being, that is all for this video. I hope it was helpful, and I will see you in the next one. Bye bye.